Hello everyone, welcome to today's webinar in the CERTIP and ESTCP webinar series. My name is Jennifer Nyman. I'm a principal at Geosyntec Consultants in Oakland, California, and the coordinator of the webinar series on behalf of CERTIP and ESTCP. I will be facilitating today's call. Today's event will consist of a brief overview of CERTIP and ESTCP, followed by the technical portion of the webinar, focusing on innovative, low-cost building automation sensors and controls. First, Mr. Julian Lamb from Paragon Robotics will present results and lessons learned from the first demonstration of a wireless building management system at a Department of Defense installation. Julian's presentation will be followed by a brief question and answer session. Next, Dr. Michael Bramley from Pacific Northwest National Laboratory will discuss the findings of a project on improving building performance using virtual air and water and air flow meters. Michael's presentation will also be followed by a Q&A session. And we will conclude the webinar today with an interactive question and answer session with both of today's speakers. Today's broadcast will be listen only. Please do submit questions during the webinar by using the chat box on the left-hand portion of your screen. You do not need to wait until the Q&A period to submit your questions, and in fact, we encourage you to submit questions in advance of that session. On this slide, we have provided a few suggestions in case you experience any difficulties with the broadcast audio. Typically, any delay will be fixed if you just refresh your screen or call into the conference line again. However, if you continue to have problems, please submit a comment using the chat box in the lower left-hand portion of your screen. With that, I would like to introduce Mr. Timothy Tatro, who is the ESTCP Program Manager for Installation Energy and Water. Before joining CERTIP and ESTCP, Tim worked at the National Renewable Energy Lab, where he focused on energy efficiency and renewable energy project development for the federal sector. Tim?
Thank you, Jennifer, and welcome everybody to today's CERTIP and ESTCP webinar. I'll be providing some background of the programs before we get into our technical sessions. CERTIP is the Strategic Environmental Research and Development Program established in 1991 by Congress as a partnership between DoD, the Department of Energy, and EPA. CERTIP's mission is to identify and address high-priority environmental science and technology opportunities with focus on DoD requirements. CERTIP funds both fundamental research as well as advanced technology development that ultimately impacts real-world environmental management. ESTCP is the Environmental Security Technology Certification Program in which we demonstrate innovative environmental and energy technologies. These investments capitalize on past investments under CERTIP or other research programs and are designed to transition technologies out of the lab and into the field. Especially important to all ESTCP demonstrations is the ultimate transition to implementation and regulatory acceptance. CERTIP and ESTCP are complementary programs with much of CERTIP research occurring in the lab and pilot scale with occasional field efforts, while ESTCP demonstrations are primarily at the pilot and field scale, although occasionally supporting lab efforts are conducted. There are four program areas in CERTIP and 5 in ESTCP. Installation Energy and Water program area is only in ESTCP, while the other 4, environmental restoration, munitions response, resource conservation and resiliency, and weapon systems and platforms, are CERTIP and ESTCP programs managed jointly by designated program managers. Our webinar today is focused on research and demonstrations that were conducted under the Installation Energy and Water program area. Installation Energy and Water has essentially 3 main areas of research. One is the smart and secure installation energy management. The second is efficient integrated buildings and components. The third is distributed generation. Our webinar series highlights research and demonstration efforts from each of the 5 program areas. As you can see, upcoming webinars will cover a broad range of topics, including energy, sustainable wastewater treatment systems, informing restoration programs for threatened and endangered plant species, plant diversity and biological nitrogen fixation in longleaf pine ecosystems, and more. You can find additional information about upcoming webinars at this link. Registration is now live for webinars throughout the end of the year. And I'd like to remind you that a copy of the presentation of today's session can be downloaded from our webinar webpage. We would also appreciate it if you could please take a moment to complete the survey that will pop up on your screen at the end of the webcast. We do use the information gleaned from these surveys regularly, and it really helps inform our content and the format in which we present this information. I'm also finally pleased to announce that the CERDIP and ESTCP Symposium will be held for the second year in a row this upcoming November in Washington, D.C. 3-day event will showcase the latest technologies that enhance DoD's mission through improved environmental and energy performance. Registration information is available on the CERDIP and ESTCP website. And with that, I hope you enjoyed today's webinar, and I'll hand it back to Jennifer.
Okay, thank you very much, Tim. And now it's my pleasure to introduce Mr. Julian Lamb. He is the founder and president of Paragon Robotics, a manufacturer and supplier of next-generation data acquisition and control products for the energy industry, including wireless data loggers, monitoring, and control systems. The sensors are used throughout the United States, Canada, and Europe for applications such as energy efficiency auditing, building performance, air quality studies, and warehouse, storage, and greenhouse environmental monitoring. Mr. Lamb has spent the last 2 decades managing multidisciplinary engineering efforts ranging from microelectronic design, embedded software, network engineering, and enterprise software development. He now focuses on leading projects related to energy efficiency, resilience, and cybersecurity facility control systems. Mr. Lamb received his degree in mechanical engineering from North Carolina State University. Julian?
Thanks, Jennifer. Like Jennifer said, I'm with Paragon Robotics and would like to step through our fiscal year 14 ESTC project regarding this wireless decentralized energy management system for DoD applications. So I'll start with defining the problem statement that we're trying to address with this technology, and then give a little bit of background into performance contracts as they tie very closely in with this technology and how it's applied at the DoD. And then a very quick background onto the topology of the system, and then really dive into the meat of the presentation on the results from this ESTCP project. So the problem we're looking at is how to address energy savings in small DoD buildings. And by small, we mean buildings that are less than 50,000 square feet. This is a big issue for the Department of Defense. Of all the federal agencies, the DoD has the highest percentage of small buildings in its building inventory. And of those small buildings, around 40% or less of those have advanced controls in those buildings. So there's a lot of energy savings that's easy to achieve just by putting in modern digital controls into these small buildings. But because of the poor return on investment for these small buildings, most of them just don't have modern controls. The high costs are due to a variety of different reasons. One is the high cost of wiring needed for retrofit applications. There's also a lot of security issues with DoD that require authorities to operate. This really prevents a lot of commercial off-the-shelf systems from being applicable to DoD applications. And as I'll get into the next slide, when tying in with performance contracts, there's a lot of additional costs for the upfront auditing and the ongoing monitoring that really add on further hardware and labor costs to the overall cost of these systems that are preventing them from being applied. So slide 19 is just a quick overview on performance contracts. The DoD is currently relying heavily on performance contracts to upgrade and improve the efficiency of many of their installations. These performance contracts are usually executed by energy service companies or ESCOs, and these ESCOs bring their own third-party financing to the table. They propose their own projects, they retrofit all of them, and then typically maintain them for the length of the contract, which can be up to 25 years. These ESCOs are then paid back with the energy savings on a yearly basis, so they can pay back their loans for the upfront financing. So this is a fantastic way for the DoD to get modern upgrades and improve the energy efficiency without needing to bring any upfront money to the table. So these energy performance contracts are typically split up into 3 different sections. There's this auditing or benchmarking phase where the ESCOs need to come in, install loggers and other types of equipment to monitor and see really what's going on at the facility before they get started. They also need to get a good understanding to calculate the potential energy savings from any sort of energy conservation measure that may be applied. They then propose and get the contract executed, and then go through and put all the retrofits in, putting in new controls and other things. And then the longest stage is this measure and verify, or M&V stage, where for the duration of the contract, so for up to 25 years, they need to monitor the energy usage and effectively prove to the government that all the savings are being implemented correctly to make sure that they get their payments every year. So these 3 stages typically require separate hardware and software systems throughout the performance contract period, adding significant cost to it. So the Paragon platform, when we started development on this a decade ago, one of the primary design goals was to be able to integrate professional level monitoring and auditing capabilities right into the same system that ends up doing the controls. So this ends up working very well for applications with performance contracts, as we can use the same overall platform and in many cases the same hardware to meet the obligations of all 3 stages of these performance contracts. Slide 21 is just a quick overview on the network topology. This is a wireless system, but it's really only wireless for the last leg. So in each of these buildings at a DFT facility, we install at least 1 or more gateways. You can see it here in level 2. These gateways have an Ethernet port, and they plug into the network, the local industrial control system network, or ICS network, at a base, and are able to communicate through that. Each of these gateways then sets up a local wireless network within the building or within an area of the building, and can communicate to hundreds or thousands of different wireless sensors shown here in level 1. These gateways at level 2 then communicate with other gateways at other buildings, and then also to a super gateway, which is kind of like a mini server at the facility that handles authentication and other high-level requirements. And then the users on site communicate with this entire system through a DoD imaged workstation, and using a browser-based interface can communicate and access the entire system. So the system is really only wireless for this last leg, and depends on the wired existing networks there at the facility. But this works very well because there's already networking typically wired between the different buildings at these DoD facilities. So we're mainly looking at trying to save the cost of wiring these individual sensors and controls in the actual building. So next I'll move on and follow these main 3 stages of the performance contracts and step through our results and what the actual installation looked like at Tinker Air Force Base, where this project was installed. And I'll mention too, we worked with Ameresco, which is one of the leading federal ESCOs working on the ESPC program. They were a key partner in this project, and so we relied heavily on their feedback throughout this process. So for the auditing, what we're looking at many different things. On the right here, this is an example of a sensor just placed into an office space. So we needed to look, we're looking at space temperatures, humidity, light levels, and motion in these buildings to understand how well the existing control system and HVAC systems are performing, and look for various energy savings opportunities around there. There's also a lot of sensors placed on the HVAC equipment. So for instance, pipe temperatures, looking at measuring the chilled water, hot water supply and returns to get an understanding of how well the equipment is performing itself, as well as a lot of sensors into air handlers and package units, looking at the airstream temperatures. And then one of the key areas is looking on the right here at current or power measurements. So most buildings have an entire building utility meter set up to get usage for the entire building. But to really understand what's going on, we need to do what's called sub-metering. So installing these low-cost power measurements at key users such as chillers, compressors, and other equipment to really understand what each of the pieces of equipment are using in the system. So here's an example of results from a gym building on the campus that we did our demonstration on. The maroon and blue curves are plotting the temperature inside the gym. So this is the occupied space temperature. And you can see this sawtooth shape. You can actually see the AC system cycling on and off throughout the day. So one of the key things we're looking at is determining if there's any sort of controlled night setback. So one of the key ways of saving energy with these controls is dialing back the heating or cooling when the building is not occupied. In fact, up to 25% of the building savings can be achieved just through night setback. So in this case here, you can see this is data from November. So this is the heating season. So this is the heaters kicking on here. And if you can see at the lower, at nighttime, you can see the system's clearly heating it and maintaining around a 68-degree temperature set point. And it's not setting the temperature back to a 60 or 62, which is achievable. So there's clearly no night setback here. These orange plots here are motion detection. So we're looking when the last person leaves the building at night and when the first person comes in the morning to understand what range of time is unoccupied and thus could potentially be set back during that. So for this ESTC project, we went ahead and we put in, I think, around 380 sensors on this 38th campus and got a very high-resolution look at all the buildings there to understand what is going on. And the end result was seeing that we had basically no advanced controls set up in any of the buildings we were looking at. One of the buildings had a set of 7 different programmable thermostats, and of those 7, 2 were set up correctly, but the other 5 were either overridden or set up incorrectly. So overall, this is an example of a DoD building set which has no modern controls. So after the data was captured, the next stage, and most ESCOs do, is look at getting simulation models built. This is really a key way of determining and calculating how much energy savings is potential with various methods. So our system, our building management system's suite of software has a system simulator software built in. So as part of this demonstration, we showed the importing of the actual data that we measured on site. And we used our simulator model to build our best guess of a simulation model, and then use the actual data to effectively tune the model and get a perfect match with the actual performance. So for those of you that have done simulation before, one of the key parts of the simulation is this final tuning, because there's so many unknowns and potential errors in the guesses made during the simulation setup. This actual real-world results are absolutely necessary to do the final tuning and get the results matching. Once these simulation models are tuned, then we can automatically run those for a wide variety of different energy conservation measures, and these ESCOs can get an actual dollar and cent value savings number that they use for their actual contract audit and move forward with that. So I'll briefly step through the installation here. There was really two stages to the installation. For the first half of this, we went through and actually wanted to make sure the retrofit controls met all the design algorithms that we'd set out and tuned them to make sure that we got the energy savings correct. The second half, though, which was arguably a little bit more important, was to look at reducing the cost of the overall installed costs of this entire system. Because we're really targeting a return on investment number, not only do we need to save energy, but we also need to get this installed cost low. So a lot of work went into things like these gateways. These gateways are installed in each building. Once we started demonstrating this and looking at the real-world limitations and requirements for these gateways and the networking connections, we spent a lot of time trying to devise the most cost-effective way or approach at putting these in different building setups. For the controls as well, a lot of work went into minimizing the hardware and also trying to speed up the engineering time needed to design and install these retrofits, as the labor can be a large portion of the overall installed cost for many of these retrofits. And this last stage I mentioned earlier was the monitoring and verification, or M&V stage. So we have a software package called MeterManager, which is our primary interface for this M&V. What it does is it takes data from a wide variety of sources, ranging from the BMS data, either the Paragon BMS or other BMSs installed there, capturing their data streams. It also pulls in data from our wireless sensors that are installed around there. We have interfaces for a wide variety of electricity and gas meters on the buildings themselves to pull in those data. And then also, as part of all these performance contracts, as they call it option A and B setups, there's a lot of manual readings that need to be taken for things like light levels and other things that are still done manually and done maybe once a year or once every quarter. MeterManager also imports all that data from manual records into the same interface. The key advantage of doing this is that these ESCOs need to verify that everything is working properly, and the faster they can catch problems, the faster they can turn around and fix them and make sure there's no issues. So MeterManager can be set up with automatic alarms and complex algorithms to be able to take data daily and alert the ESCO or operations and maintenance personnel on site there to any problems that would affect the energy usage. On the cybersecurity side, this is, I could spend an entire webinar going through this itself, but as part of the any of these industrial control systems, the DoD now requires an authority to operate. This process was a key objective of this project starting early on. It took about 2 years overall from the time we started to the time we actually got our ATO approved in May of last year. A lot of work went into not only just the paperwork and the logistics of getting the ATO package through the process, but we also took the opportunity to make a lot of improvements to the software systems and hardware to make sure that the system was secure and really met the Air Force's requirements and DoD requirements the best possible, and make a very flexible system that could address their concerns going to in the future. One point to point out, this is we achieved a site authority to operate for Tinker Air Force Base. We are currently working with other bases and other branches for a similar process for other sites, because these site ATOs are required for each installation you install it on. And I'll mention at the end of this presentation, we also have a new fiscal year 18 project looking at generalizing this platform and getting a type authority to operate in the future, which would allow this to be applied at other branches and other installations much easier. So one of the results here, this is the results from 4068, which was one of the smaller buildings there. So we use full M&V methodologies that ESCOs would use to show the actual measured daily savings, energy savings here. And our results were quite good. We saw 26% metered electricity savings for the entire building. So this is not just the HVAC usage, this is the entire building, capturing lighting and all the other effects there. And on the gas side, we saw almost half the gas savings from these modern controls. The installation costs were also analyzed here. So we split this up into two sections. One of these small buildings that are thermostatic controlled. The lowest cost competitor out there is really a wireless Zigbee system that has a backnet interface there. But our analysis showed that we're roughly half the cost, the overall total installed cost of this system on the small buildings here. On the larger buildings, really the most cost-effective is still a Niagara-based J system. And although our cost advantages drop a little bit on these larger buildings, we still show around a third of the cost savings versus a typical Niagara system on this. So although the costs here, once we got into it, were a little higher than we initially anticipated just because of the extra overhead and costs working on DoD facilities, we were able to get a little bit more energy savings than we initially anticipated as well. So the end result, the end target for most performance contracts, as a rule of thumb, is a 10-year simple payback. That's usually enough to automatically allow funding using performance contracts. So our target was anything less than 10 years, and we were able to achieve around a 7-year, a little bit better than 7-year simple payback across this entire sample of demonstration buildings. So this chart here shows all the buildings on the 38th CEIG section of the Tinker campus that we use for the demonstration. Although we only, even though we audited all of these buildings, we only retrofit controls in 6 of them. So these results here show a combination of actual metered or simulated utility savings from the proposed control retrofits. And then the installed cost was from our data. We actually did time studies and at the end of this project to determine a true installed cost with all the, basically the true cost that an ESCO would pay for these to calculate the simple payback. So of all these buildings, 2 of them had just barely over the 10-year limit, and then this one building down here in red was a warehouse which had heating only and had no network connections, so it was kind of a worst case scenario. There's really not a lot of savings, and the cost of installing the new controls there was quite high. But the key takeaway is that the overall, the mixed simple payback for this entire section of buildings was less than 7 years. So most ESCOs would go ahead and propose to bundle all these together and do a retrofit across all of them and just absorb a little bit of the extra cost for some of these buildings that may not meet the ROI, but get a nice system installed there to improve operations and maintenance and modernize the controls here. A few other points to mention. This is Tinker Air Force Base, which is down in Oklahoma City, which has surprisingly low energy costs. Their electricity is at 5.5 cents a kilowatt hour, and gas is at 49 cents per therm. So these are on the very low side, typically in the continental U.S. So these numbers hopefully should be very conservative, and the simple payback should be greater in other buildings. As part of a separate project, we've also gone ahead and audited 140 other buildings at Tinker, and we've seen very, very similar results to these. So we have very good confidence that these ROIs should be very applicable to other bases as well. So moving on to commercialization, our hardware and most of our building management system software pieces are now available off the shelf. As part of this demonstration, we realized that we really needed to add in some service offerings. So we have some M&V service support offerings, as well as the controls design side of things to add to this and create a little better package for ESCOs or prime usage. But our primary sales channel for this building management system is for ESCOs and utilities working towards using performance contracts on DoD applications. We're also doing a few small projects as prime for DoD customers on the meter data management side of things as well, outside of the performance contracting scope. So next steps, we're looking at a lot of work now on energy resilience. So we have 2 ongoing DoD demonstrations tying in advanced microgrid controls into this existing wireless building management system platform because it ties very closely in with building management systems and being able to adjust HVAC usage for the resilience aspect and getting the load shedding. It works very well together. We're also working now on scalability of the system. Even though we demonstrated it on a set of buildings, around 15 buildings, there's been a little bit of some limitations on scaling this up to an entire base. So there's work now on getting some of the issues hardened to be able to handle that. And then I alluded to earlier that we have a new interesting fiscal year 18 ESCCP project looking at adapting our platform into a generalized host type system to allow third-party hardware and software manufacturers with energy savings or industrial controls equipment to be able to plug into this environment and eliminate the need for getting a separate authority to operate. So as I'm sure many of you know, the security and the RMF type issues surrounding the ICS systems can be a big hindrance to the acceptance, and so this is going to be another key way of trying to get these systems in place faster at DoD facilities in a secure manner. So in conclusion, the overall results of this project were extremely good. We were able to show that even on very small buildings, we can get the necessary return on investment needed to justify this platform for DoD usage with performance contracts. And we're continuing to expand this for the scalability, implementing resilience, and then also the security ramifications, trying to improve that process to make it more quickly applicable for other sites. So please, if there's any questions after this webinar, please feel free to email me or give me a call to ask questions or discuss other applications. I'll be more than happy to address those. Thanks, everyone.
Excellent. Thanks, Julian, for the very informative webinar. We received a large number of questions from the audience, and we'll start addressing those now. The first question is a clarification. Are you only monitoring equipment status, or are you using any remote commands to change equipment behavior?
The controls, so we're actually putting in full controls in these buildings, so retrofitting the control capability. So for smaller buildings, that's thermostatic controls, so replacing the thermostats with new Paragon wireless thermostats. And for larger buildings, actually replacing the air handler controls, chiller controls, boiler controls with those with new Paragon controls or integrating with their existing ones. So we're looking at both monitoring and controls for this. And you mentioned remote, but these are all done locally where the DoD doesn't like remote access, and so these are all on-premise solutions typically.
Great, thank you. Your results showed approximately 25% electricity savings and 50% gas savings. Do you have an idea of how these savings were achieved? Was it from applying setbacks or overriding local control, continuous commissioning, or other things?
It's a good question. The data I showed there was actually the worst case. Those are the small buildings, which are just thermostatic control. And for those, there's by far the largest mechanism is the night setback and the unoccupied setback during holidays and other days that can be done. There's also some savings in there from humidity adjustment. We have humidity sensors in all of ours, so we can apply some slight skewing using the human comfort model based on the humidity to make some savings. But beyond that, for the smaller buildings, that's around all the typical savings you can do other than adjusting some of the cycle times on the package units. For larger buildings with air handler controls, there's a lot more available. So there's blower shutdowns. There's outside air temperature resets for boiler and chiller supply. So the savings actually is even higher, about 5 to 7% higher on the building basis for larger buildings because of the extra savings potential on those buildings.
Okay, thank you. Is there a way to quantify the potential cost per square foot of a building to deploy this kind of network, understanding variability in building size and complexity?
Yes, it's a good question. And that chart I showed on the overall payback, that would be a very good starting point. I think there's the square footage listed there and the overall installed cost. So if you look at first making sure the building is categorized into a small or larger building, and then you utilize the cost per square footage for that classification, you can probably get a very good idea of a good starting point for the per square footage cost for the installed system.
Okay. And an attendee from EPA noted that personnel costs are typically much higher than the energy costs in buildings, and asked what algorithms or policies have been incorporated to help ensure comfort, human health, and productivity are not adversely impacted, and thus offsetting the energy savings.
Yes, good point. And so part of this demonstration was actually looking and working with occupants at Tinker there on this demonstration building site to effectively try to get more data to understand what was a good level to maximize savings but still not cause complaints. And this is actually a little bit self-regulated, a little bit with performance contracts many times because these DESCOs are responsible for the ongoing maintenance and handling support calls in there. The more calls they get from people that are uncomfortable, they end up paying for it with the maintenance side of things. So that was another kind of key result from this, was really dialing in and understanding what a reasonable level of night setback and comfort ranges during occupied timing to maximize that. But again, a lot of work. We understand that's variable based on people. So the system is set up with a little bit of adjustability on a window, so the humans, the personnel that are inside these buildings can make minor adjustments to the comfort within a band, but we still limit overall movement of those comfort levels outside of that band. Of course, those can also be retuned or reset up by the ESCO on site, and we make it as easy as possible to make those tuning adjustments later on as needed. So you're right that it's always a battle between the energy savings and the comfort, but we're trying to make the system as flexible as possible, as well as use this demonstration data to kind of give a good benchmark for what's feasible.
Okay, thank you. Could you explain a little further whether you're, with this system, tying directly into the building automation system or always using passive sensors?
It ties directly in. There's a mix. So for the M&V stages on these performance contracts, there are many sensors that don't actually tie back in and I guess considered active control. A lot of them are just monitoring and looking at checking power usage and other things. It may set off an alarm or show up in a report, but it is not actually used minute by minute for the controls. But for the actual controls of these buildings, there is, we're using all the same typical inputs that are needed for any other types of controls in those other systems. So it's a fully active system on those subset of systems there. And I can get into more details on it varies obviously based on all the different building setups out there. But typically for larger buildings, we either retrofit the controllers with some third-party controllers and then tie in and utilize our system as kind of a master high-level control that's splitting the low-level safety type controls with the high-level energy savings algorithms. Or for some cases where they don't want to do a complete retrofit of the controls there, we can tie in via BACnet or other types of LAN or other interfaces there to provide some minor energy integration with it for some small savings, but saving on the overall installed cost because most of the equipment can be salvaged.
Okay, thank you. Did some of the Paragon monitoring equipment remain in place for ongoing monitoring at the Air Force Base and for monitoring persistence? And was that incorporated in the costs that were shown in the presentation?
Good question. Yeah, so about half of the sensors, let's say they go in and audit a building, if that building does end up getting a retrofit controls in there, about half of the sensors are typically able to be left and integrated into the system. Some of the sensors there are either duplicate. For instance, maybe there was a space temperature sensor in the offices to monitor what was going on there, but then for the controls, we would be replacing that with a thermostat or some sort of wall-mounted control unit. So they would go back and remove the temporary temperature sensor in place. So it's about half is left in place if they end up using or retrofitting controls. In some of the buildings, they may not end up doing anything, and they would rip out all the controls. But for all other cases as well, so a lot of the sub-metering and even whole building metering that we put in, kind of a low cost current transducer method where we're just looking at current usage. So it's not a true power usage number, but it can get pretty good data. Those we end up, even though they're battery powered, we end up putting those in as a permanent sensing type meter sensor set up in many of these buildings as well, and just incorporate battery changes into the maintenance, typically replaced every 5 years.
Okay, great, thank you. We have time for just one more question before we move on to the next presentation. Are your simulation models based also on historical weather forecasts? Is historical weather incorporated into the simulations?
Correct, yes. So as part of all of the standard M&V methodology, you look at a typical meteorological year. So the data factors in data it's pulled from the NOAA site to actually get on-site data there, or we can utilize data streams from Paragon sensors or other sensors placed out there. So yes, that is fully factored into the simulation. And then when they're looking at the calculated savings, they typically scale those all for a typical meteorological year as well. So climate is definitely taking no effect.
Excellent. Thanks again, Julian, for the presentation and answering all of the questions. And to our audience, Julian will return at the end of the webinar to answer additional questions. If you have more questions for him, you can note that in the chat box when you submit the questions. So next we'll move on to our second presentation. And our second speaker is Dr. Michael Bramley, a staff scientist at Pacific Northwest National Laboratory. He has over 30 years of academic and research experience related to energy technologies and policy, focusing on advancements in control, automated fault detection and diagnostics, and self-healing systems. Dr. Bramley has served in a variety of roles, including principal investigator and research contributor, project and program manager, department chief scientist, and the leader of several initiatives. Most of his work over the last 25 years has focused on improving the actual operating efficiency of buildings. He earned his bachelor's degree in mechanical engineering from the University of Pennsylvania and his master's degree and doctoral degree in engineering sciences from the University of California at San Diego. Mike?
Thank you, Jennifer. I'll be presenting on the use of what we call virtual flow meters for improving building performance, particularly the heating, ventilating, and air conditioning systems. I want to point out that I'm a participant in the project, the ESTCP demonstration project, as well as the original development of the underlying technology. but the overall efforts in this area have been led by Professor Lee Song of the University of Oklahoma. I'll be presenting the problem that we're trying to address, a description of the technology, some of the results of the demonstration, and then finally conclusions. The problem we're addressing is the fact that general metering that's provided is at the whole building level. We may measure natural gas consumption, we may measure electricity consumption at the whole building, but to understand the condition of equipment and its performance, we need to collect data that gets down into the details of the systems. That's the purpose of developing this technology. So what we're trying to do in particular in this effort is to introduce flow meters that are generally expensive to purchase and install. The installation process is usually intrusive. That is, it may involve stopping processes while you're doing the installation so that things like penetrations and pipes can be made. And finally, measurement of flow rates requires long and straight sections of ducts and pipes, both before and after the point at which the measurements are made. So what we're trying to do is to substitute low-cost sensors for these more expensive flow meters so that we can monitor the performance of the systems and equipment more carefully. We do this by introducing these virtual measurements where we essentially measure a set of variables that can use low-cost sensors. Several of these may already be being measured. These are the X's in this equation under virtual measurements. And then we fit curves that represent the performance of devices to data from the specific equipment and systems to ensure that we're modeling, or we have a model that represents the actual equipment at each point in the system being monitored. This provides us the capability after we train or calibrate this model to the specific equipment to calculate measurements at those points, or effective measurements at those points, and we refer to these as virtual measurements. And the methodology is virtual sensing. So, as I pointed out, we use low-cost sensors to create fan and pump flow meter models and valve flow meter models, or flow meters. This enables us to continuously monitor performance down at the system level or subsystem level, and it allows us to detect performance degradation and faults in the equipment so they can be corrected as they occur and maintain the performance at its peak level. The diagram at the bottom, if I could get you to focus on just the components in the boxes and the dashed lines. The dashed lines represent physical connections, and I don't have all the connections shown here, but the major ones. So on the left we have chillers providing chilled water that goes to the air handling units. On the right-hand side we have boilers that are providing hot water to provide reheat to the terminal boxes in the system that the air handling units provide air to, cooled air to. Now, if you can now look at the solid lines represent the data collection and control system. You see the building automation system in the box at the top. And you see a number of circles with letters in them. If you refer to the key on the right, the capital letters C and H next to the chillers and the boilers represent overall measurement of the flow rate of chilled water from the chillers to the air handling units, and measurement of the reheat hot water from the boilers to the reheat coils in the terminal boxes. There's also a measurement of the supply airflow rate coming out of the air handling units, represented by the type 2 virtual meters. This is a virtual airflow meter. We also, although not shown here, for air handling units that have return fans, we also have measurement of the flow rate of the return air. So I'm going to go through how we determine these virtual measurements for each of these types of meters. The first is virtual flow rate measurement using valves. I'll get to the fact that we can use this as a virtual energy meter in a minute, but for now let's focus on measuring the flow rate. If you focus in on the diagram of the system here in the middle of the page, you'll notice at the top we have a valve command from the controller going to the control valve for the chilled water for an air handling unit. That signal also goes to the box at the top right of the diagram that's labeled virtual meter. Virtual meter is nothing more than the algorithms running on some processor. So basically I'm describing the algorithms that are implemented in that box. We also add measurement of the pressure difference across the control valve. This is used then in the virtual meter along with the valve command to determine the flow rate. In addition to that, running inside the virtual meter is a flow rate equation that we fit to the valve itself, the specific valve itself. This is indicated by the equation below the diagram. Qx, which is the flow rate, is equal to F, which is a function of X, which is the valve opening position, times the square root of the pressure difference across it, delta P. And F is the valve characteristic that changes as the value of the opening changes. We determine F through a training process or calibration process in which we measure the pressure difference, we measure the flow rate using a temporarily installed sensor, in this case well, I'll show you this in just a minute. I'll show you the sensor in a minute. To determine this function f of x. We then, after training, put f in there, we measure delta P, and for each delta P, we then can calculate a virtual value of Q. Oh, I want to go back because I want to point out that on the right-hand side of this diagram is a picture of the chilled water supply temperature to one of the air handling units. At the top in the circle, we have the DP measurement, or actually the pressure taps. And if you look carefully, you can see copper lines coming out of each of those. They then go to a transducer that actually measures that pressure difference and then provides that to the virtual meter. At the bottom on the right, or in about the center of the bottom, is the chilled water valve controller. I don't think you'll be able to see the valve itself there, but it's there. This is the actuator for the valve, so the signal goes to that actuator, and that's the signal we also take to the virtual meter and use it as input. The other type of virtual meter we have is a virtual pump or fan flow meter. The diagram for this, if you'll focus in on that, takes a VFD speed signal or frequency signal that comes from the controller that goes into the VFD, so the VFD responds by providing the corresponding frequency. We also have power measurements and voltage measurements coming out of that. Those two measurements, along with the VFD speed command, go to the virtual meter. In addition, we also measure the pressure difference across the fan or the pump, indicated by the red DP and the lines coming off of the pipe or the duct in which the fan or pump are located. That measurement is also taken and input into the virtual meter. And actually what we input is the head produced by the pump or the fan. Combining those into a flow rate equation that again is fit using training data to the actual device, we can then determine, and this is used to model the motor efficiency and the fan pump efficiency as a function of conditions. We then have an equation once we're done training for flow rate as a function of the variables coming into the virtual flow meter. So that for any measured conditions that we get primarily from the DP and the VFD, we're able to determine a virtual value for the flow rate. So we've taken this technology and we've demonstrated it in a 3-story outpatient medical clinic at a DoD installation. You can see the characteristics here. Floor area about 160,000 square feet. There are 13 single duct air handling units with hot water reheat. The central plant has 2 chillers and 2 boilers, and there's a building management system that provides direct digital control. There are actually 13 supply fans, 1 for each of the units, and 2 of the air handling units do not have return fans. So we have 11 return fans. For all of these fans, we install virtual fan flow meters. I'm not going to dwell on the diagrams a lot. On the left, we have a picture of the air DP sensor. In the middle, we have the picture of the VFD display. The VFD data are taken in or communicated to the virtual meter. And I do want to point out on the right that this is the supply duct, or the bottom of the supply duct of the air handling unit. We temporarily install velocity probes across the cross-section of that duct and make velocity measurements that allow us then to calculate the flow rate through that duct. The inset on the lower right-hand side is a mounting bracket for the probes that make these measurements, and this enables us to install the probes entirely from the outside of the duct. There are fingers on this device that are hanging down in this picture, but they go up through the hole. When you insert the probe through the middle hole, it forces the fingers out, which hold the mounts inside there, and then we have some set screws for the probe to adjust its penetration into the duct, and we have some 3 screws that allow us to align this so it's perpendicular with the flow. Okay, the other type of flow meter for the water side is the valve flow meter. We take the same approach. We apply it to the valves. We've installed 13 of these, 1 on each of the chilled water supply valves to an air handling unit. We use an ultrasonic meter shown in the right-hand picture during the training process to provide the actual flow rate through that. We consider that ground truth coming in. And then afterwards, we remove this ultrasonic meter, we move it to the next unit, and we apply it again. So we need only 1 ultrasonic meter. On the left-hand side, you see some equipment used for measuring the delta P in the foreground, and in the inset photo on the left-hand side, you see the controller for the valve. We've installed pump flow meters for the pumps indicated here, 3 primary chilled water flow meters, 3 secondary chilled water pump flow meters, 3 condenser pump flow meters, and 2 secondary hot water pump flow meters. This allows us to monitor these flows through virtual sensing. To give you an idea of the accuracy on the water side at least, we have a plot here of the water flow rate versus time for a period of 2 days. The blue line represents the measured values, and this is using the ultrasonic flow meter. The calculated values are the virtual values, and you can see that there's excellent agreement except that the peak values around the middle of these of each day of these plots. Overall, this is excellent agreement. This is an indication of the accuracy of the valve flow meter. You see flow rate here plotted against time for a period of, what's this? It's about a day, a little less than a day, it appears. And there are 3 lines shown. The 2 I want you to focus on are the blue line that represents the data from the ultrasonic flow meter, which can be viewed as the correct flow rate, and the red line, which represents the state of the virtual technology now. And these are the virtual sensed flow rates at the same time. And you can see that the agreement is within plus or minus about 0.1 gallon per minute. The variation, the rapid variations are not important for us to capture, but you can see that they're generally, the virtual values are generally within that amount, 0.1 gallon per minute of the ultrasonic flow meter measurements. The black line was an early model used for the valve, and you can see that was not nearly as good, and therefore we had to make an improvement in that model. So that's the technology. And now I want to turn to an application, which is detection of faults in the equipment and systems using these virtual meters. There are 4 categories of faults that can be detected using this technology. Outdoor airflow control faults, for example, a stuck outdoor air damper, the minimum position for ventilation only of the outdoor air damper being incorrect, and related faults. There's also fan operation faults, which I'll show you an example of, reheat control faults, and pump operation faults. And each of these represents a set of faults. I'm going to show you first detection of a loose belt fault. You can see a representation here that's from a building automation system. On the left-hand side at the bottom in the diagram, you see return air coming back from the spaces. In the middle branch that's rising from the main branch there, you see the outdoor air intake and associated controls. As you move to the right along the lower branch, you see heating and cooling coils, filter and so forth, and leading to the right is the supply air temperature after being cooled. What we can do to detect a loose belt is to monitor the frequency from the VFD, which is a representation or a surrogate for the fan flow rate. Blue represents the frequency command, that is the speed being requested of the fan. And the red represents the virtual calculated frequency based on the power and head that are measured from the VFD. As you can see, up to about 11 a.m. on 7/19, there's a nice match between the frequency command and the calculated frequency from measured data. As we proceed, and there's an increase in the frequency command requesting a higher flow rate of air. The red line does not keep up with the request. This is an indication that the belt is slipping. The velocity of the fan is lower than the velocity being requested, and therefore is an indicator of a loose belt or slipping belt. The second example of a fault being detected that I want to point out is a case where we implement a change in the set point for the differential pressure set point for this chilled water set pump. So we're mimicking, in a sense, a override of this set point that was either intended to be put in place temporarily and then put back to its usual value, and that was neglected and it was maintained in place, or someone reset that set point to an incorrect value. What we see in the plot is the pump head in PSI versus time for about a week-long period. The blue line, again, represents measured values of the flow rate, and the orange line represents the calculated or virtual values of the flow rate that correspond to normal operation. The fault was implemented at the beginning, the left-hand side of the arrow, the red arrow. That's when it was implemented. You can see the measured value increase, the normal value staying the same, and this continues throughout the rest of the time history shown here. This difference shown here is an indication of the fault being present. Okay, shown here is a set of results for one air handling unit on which there were four faults identified. The two that I showed you where there was an actual override of the set point, plus two others. And we have a plot here of cooling energy use in kBTUs per hour against the outdoor air temperature. The gray points represent prior to fixing the problems that were identified. The yellow represents after the faults were repaired. And you can see roughly that the gray points on average are higher than the post-correction yellow points at the bottom. In fact, the gray averages roughly about 80. The yellow averages roughly about 50 kBTU per hour. The difference represents about a 37.5% decrease in energy consumption for this specific air handling unit. I want to now turn to savings for the building overall. This data represents monthly data from 2014 through the middle of 2017. It's kind of difficult to see the savings on this, so I'm going to move on to the next plot where we plot the same data on a monthly basis. We have electricity on the left, natural gas on the right figure. Each point represents a month. Red are for months before. Green represents months after. And to estimate the average difference, that is improvement associated with correcting faults identified using this technology, we regress on the two sets of points and determine the average difference between the two lines. We found an average electricity consumption reduction of 13% for this building and a 25% reduction for the natural gas consumption for this building. So, in conclusion, the benefits of virtual meters, as we've seen a little bit of, are, first of all, low cost. We're using low-cost sensors in place of much more expensive sensors. We don't need the space ordinarily required for the physical sensors to be installed, which is sometimes a problem with HVAC systems. We improved the monitoring capability of the buildings by adding flow rate sensors where we had none before. By the way, I never got back to state that any of these flow rate measurements can be converted into energy flow measurements by adding measurement of the temperature difference between upstream and downstream for the medium. So for the water flowing through or the air flowing through a fan. So it improves monitoring capability. In turn, it enables providing energy efficiency by keeping the equipment operating in ideal conditions. And in this case, overall, we've measured a 16% savings on whole building annual energy use. And this was for a LEED Silver building. And finally, I want to conclude just by pointing out that our main message is that by using these low-cost virtual meters, we enable high-resolution monitoring of buildings, at least higher than was present previously. And this enables us to make cost-effective fault detection and diagnosis, greater energy efficiency by correcting faults and monitoring performance that leads us to correcting degradations, and lower energy costs. So with that, I'd like to turn it back to Jennifer.
Thank you very much, Mike. We have received a number of questions for Mike's presentation today. The first question is from the Navy. Will electromagnetic interferences, especially when using the VFDs, affect virtual data flow measurements?
That's a good question. Well, I don't have data on that. I do know that we improved our motor models by eliminating harmonics. I don't know if those harmonics originated because of electromagnetic interference or not, and I don't have data indicating how much electromagnetic interference would affect the VFD data. However, we do have data comparing independent measurements of the power coming off the VFD against the VFD measurements themselves, because there was some question regarding whether the VFD measurements would be accurate enough. And what we found was that the VFD measurements were very, very close to the independent measurements of power and frequency, so forth.
Okay, thank you, Mike. Next, would you please explain the differences between the virtual meters and program logic controllers, or PLCs, that are available on the market? And what are the key advantages of the virtual meters?
Well, you can't do anything with a PLC that you don't have a sensor for. So we're not really competing with PLCs. In fact, although we haven't implemented it this way, it should be possible to implement the calculations behind the virtual metering in a PLC. We don't do that presently, though. So I don't look at those as competition. I look at the virtual sensors as a replacement for sensors that there may be resistance by the owner to invest in. And this is something we've seen in many, I'm going to refer to them as commercial buildings, but I think they apply across to DoD installation buildings as well.
Okay, excellent. Thank you. And we have received a couple of questions about cost. Do you have a comparison of the installed cost of the virtual sensors versus the other kinds of more traditional sensors?
Yeah, I wish we did. We have six months going in the project, and the cost analysis is being done during these final 6 months. But we do have some preliminary data that we've made some simple calculations on. And based on this particular installation, and we need to keep in mind that this is one building only, the results tend to show that the payback period for the virtual sensing based on this particular building would be 2 or 3 years. This is a 3-year-old building. It's a LEED Silver building. It should be in good operating condition, yet there were many faults on it. An older building would likely have more faults. A lot depends, though, on the cost of the virtual metering system, how many points you have to put in, how many sensors you need to add because they're not there already. Physical sensors, even though they're low cost, the cost adds up as you install more of them to support the virtual sensing. So that's really the best I can say, except for the fact that we did make a comparison between the cost of installing the virtual sensing equipment, which we did install except for the VFT, our own sensors to support. The cost of physical meters is approximately twice as much as the cost of installing what's required for the virtual meters. We will be determining, I'm sure, more accurately the kind of information you're looking for. We just don't have that now. And if you want to know more about the status of that, send me a note. I hope you have my email address off the slide. And I will put you in touch with Lee Song, who leads the overall effort. And she may have some additional information on this.
Okay, thank you very much. And we do have that contact information shown on the screen right now.
Thank you.
Does the model have to be recalibrated for each building, or can you calibrate based on a given piece of equipment and extend that to similar equipment in other buildings?
We have not explored that, but we don't recommend it because there's differences in the age, the wear, sometimes the model numbers, although you could do it by model number. And there's effects of the system around it, around the device, like a valve or a pump or fan also. So we recommend that an individual fitted or trained model be developed for each of these physical devices that we base a virtual meter on.
Okay, thank you. And we have two more questions for you, Mike, before we bring Jillian back. The first is, would you recommend this technology be applied to small buildings with packaged air conditioners and heat pumps?
Well, in principle, the methodology can be applied to packaged air conditioners and heat pumps. But we have developed this technology, this implementation of this approach, this technology, for build-up systems that have boilers and chillers and air handling units, and in this case, variable air volume system for distribution, so VAV terminal boxes with reheat. So we have not applied it to packaged equipment, but the methodology would apply. So it could be adapted by someone to air conditioners and heat pumps.
Okay, thank you. And then one last question for you, Mike. Could you summarize what you see as the next steps for this development effort for this technology?
Okay, there's several next steps. From a technical standpoint, we are still collecting monitored data that will add to the data we have available to more definitively calculate, identify the savings that have been achieved in this building. We are looking at a number of different deployment or dissemination opportunities that range from embedding in building automation systems to, in a separate effort, University of Oklahoma has developed a package that would facilitate easier implementation of the virtual sensing. And I'm not free to talk about that right now, but again, Professor Song would know more details of what she can reveal about that and not. And my understanding is that the algorithms themselves will be published in the literature and available for any developer to use, including controls systems integrators and control system manufacturer vendors. We're also making contacts with utilities as well to see if there may be opportunity in their programs. So really a full spectrum of different approaches to getting the technology out and used.
Great. Thank you, Mike. At this time, we'll bring Jillian back, and we'll have we have a couple more general questions that we'll ask both of our speakers. So the first question is, in the absence of an active performance contract at a facility, what are some of the key benefits to implementing improved metering? And Jillian, we'll start with you. Julian, are you back? Yes, there we go.
I am, sorry. Yep, I guess there's twofold I mentioned. One is for ongoing metering at facilities. One of the biggest concerns with metering programs is really the quality analysis of the data, making sure that any bad data is captured and found. So one of the best ways of doing that is to be able to integrate existing meter data into a single system, as well as being able to install key sub-meters or other duplicate meters at key facilities and integrate those and be able to get software to be able to automatically start looking for issues. So for example, if you have one full building meter and several sub-meters, the system can sum up the sub-meters and check that against the whole building meter to look for any issues there. So there's a lot more QA you can do with an integrated system such as our MeterManager system. The other one is to implement things like the climate adjustments. That's typically not done with a lot of DoD systems. They're just looking at collecting the data. So it's not the best information for running baselines or understanding the impacts of changes to the equipment or to missions. So being able to incorporate climate adjustments into the data is another key benefit.
Okay, thank you very much, Julian. Mike, do you have anything to add?
I don't have much to add, but I want to point out that I think that our two technologies are not competitors with one another, but actually complementary. Although Julian and I haven't discussed this, our algorithms could actually be incorporated into their system if Julian wanted to do that. So they could be another way of using the data. Our algorithms in our virtual metering are all automatically operated, including the fault detection, degradation detection. They're done automatically. They're done continuously using the right data from the physical systems and the sensor systems. So that's why I view them as complementary technologies.
Okay, thank you very much, Julian. And as we wrap up today, I'd like to ask each of our speakers today, what is the last message you would like to leave our audience with? And Julian, we'll start again with you.
Sure, I'd just say, yeah, there's a lot of good technologies out there. So if you're a manager or others with DoD, definitely reach out and figure out the best application here to get some energy savings in there. There's obviously a lot of work that needs to be done for DoD applications, but there's definitely technology out there and approaches that can help save energy. So start the conversation, I guess, would be my takeaway.
Wonderful. Thank you very much, Julian. And Mike, what's the last message you would like to leave everyone with?
Yeah, I just want to point out that I think the technology that I described is an opportunity at lower cost to improve the monitoring and control and maintenance of your HVAC systems. And it can be done at lower cost than it might be done using purely physical sensors. Your current BMS supports monitoring and graphing trends over time for variables that are measured. The number and variety of flow rate sensors, though, is quite limited in systems generally. There are exceptions, though. And the BMS can provide alarms, which are most commonly used to alert operators when specific variables go outside of normal bounds. But fault detection diagnostics, degradation detection are more complicated than single variables. So most BMSs, not all, but most don't provide these kinds of capabilities for fault detection and diagnostics and degradation detection. So I want to point out, this is not a fundamental limitation of BMS technology. It's just a matter of what's made available by the companies providing these systems. And in some cases, these capabilities are available, but usually are not made available to the client because the client doesn't want to pay for them. So I think these sorts of capabilities can be embedded into BMSs, and that includes, I hope it includes the one that the sensing system and the capabilities behind it that Julian described. So In closing, I just want to say virtual sensing enables measurement of values for variables for which physical sensing is generally not available, and because it's expensive. And many owners are unwilling to invest in it. So technology provides an inexpensive way to increase the resolution of monitoring of equipment and system performance and the condition of the equipment, and enables what we might call condition-based or even predictive maintenance of your systems that will save you energy and save you money.
Excellent. Thank you very much, Mike.
Thank you.
With that, I'd like to thank both of our speakers today. Thanks for the informative presentation and for addressing all of the questions. In the webinar series, our next webinar, as Tim mentioned, is on Thursday, August 9th, and is titled Energy Sustainable Wastewater Treatment Systems for Forward Operating DoD Installations. And that webinar will feature Dr. Catherine Guy of the U.S. Army Engineer Research and Development Center and Dr. Bruce Logan of Pennsylvania State University. Registration is open for this webinar, so please visit the CERDUP and ESTCP webinar webpage. And you can register there for this and other future webinars. Before we conclude today, I would like to remind you that both the audio and a copy of the presentation of today's webinar will be archived on the webinar webpage in case you would like to refer to them in the future. We would appreciate it if you could please take a moment to complete the survey that will pop up on your screen at this time. This concludes today's webcast. Thank you.